Hey everyone, welcome back. Another week of Gears and Gadgets. Uh, we're going to be starting here, essentially with the same circuit we ended on last week. Three LEDs, three 220 ohm resistors in series with each of those LEDs, going back to negative. And the only difference is this week we have our supply high pins plugged into 9, 10, and 11. Those are digital pins 9, 10, and 11, and you'll see those numbers have a little squiggly mark next to them called a tilde. That indicates that those pins can approximate an analog output signal, and that's what we're going to be playing with right now. So you can see this LED isn't just on or off like they've been all through last week. This is actually fading on and off, sort of emulating something analog. What I mean by that is thus far we've been working with a digital signal, either on or off, 1 or 0, high or low. In this case, 5 volts being high, 0 volts being low. Now we're going to be playing around with approximating an analog signal, something that can exist in between those two values. And we're going to be doing that with this same series of LEDs. So just make sure they're in pins 9, 10, and 11, the ones with the little tilde, the squiggly mark next to them, and we'll get started with the code. So here we are in the code in the Arduino program. I'll be emailing this to you so you can copy and paste it either from a text file, or if you want to take the Arduino file and open it up yourself, you can do that. Let's start at the beginning. We've got our integers that are designating which pins each one of our LEDs is connected to. That's all these are standing for, so our new integer variables here now stand for 9, 10, 11. So that helps the computer understand where it's going, helps us change where those are after the fact, and makes our lives generally easier. Here we have the brightness integer. Now that's going to be something we use later in the code for determining what level of power we're going to give to the LED to make it light up or fade down. And then lastly, we have a new integer called fade, which is the increment by which we need to increase or decrease the brightness of the light width. This, whatever your fade number is, just make sure it divides evenly into 255. The values for this are going to exist between 0 and 255. That's completely on and completely off. So when we get into the setup, we have our pin modes, setting our LED pins to outputs, and the first thing we're going to do is digital write the LED pin on and off for a half second. I put this in here so that you know when the code begins. It just gives a quick flash, but it also shows you the difference between a digital write command and an analog write command, which we're going to be going to next. The digital write command is high or low. High, low, they light up blue, those are the special words, and down in the loop we have something called analog write. Now analog write can only happen through the digital pins that have the little curly Q next to it, the tilde. Those are pins that can emulate analog signals. And now in the loop we're going to be telling it to write to the red LED the brightness value. Now at the offset the brightness value is 0. We set that up at the top. But as it goes through the loop, the next line tells it to add the fade value to brightness. So it's going to increase by 5 until it gets somewhere, 255 being the maximum. Here's the new thing, the very new thing that we have to deal with this week is an if condition statement. If the brightness is less than or equal to 0, or these two vertical lines, vertical bars, which you can make by hitting shift and backslash, two in a row, means OR to the Arduino. So if the brightness is equal to or less than 0, or the brightness is greater than or equal to 255, do something. This is a condition that it checks every time it goes through the loop. So every time it goes from analog write to the brightness addition, it says, hey, is it at or equal to 255? Well, if that's the case, then fade becomes negative fade. So now we're going to be subtracting. This delay outside the loop is just a little bit of a delay so that we can perceive the change. The smaller the number, the faster the fade. The larger the number, the slower the fade. And so if we look at this, starting at 0, inevitably, we will get to 255 as our number. When that happens, fade becomes negative fade. The next time through the loop, 255 is subtracted from by 5 instead of added to. So when that continues on in the loop, it'll get to 0, and then fade, which is already negative, will become a positive because a negative of a negative is a positive. So that's what lets this fade in and out perpetually.
So here's the circuit for the next bit of code we'll be working for. It's essentially identical to the last circuit from last week, again, except we're using pins 9, 10, and 11. And it's identical to the last piece of code for the single LED, but now we're using 3. And this can be 3, this can be as many of these as you have digital pins with the tilde sign next to them that can emulate analog signals. So this is 3 LEDs emulating 3 separate analog signals and fading in and out together. Let's go check out the code.
So here's the code for the second fade circuit. It's very similar to the first. We still have our output settings in the setup. We've still got a digital write blink for the red LED when the code starts and starts over. Only happens once because it's in the setup. And the loop is exactly the same, except now instead of just having one analog write command, we have 3 analog write commands. So every time through the loop, it's writing each of these to the brightness level that's set up inside of the if condition. The if condition is super important. This is checking for this set of parameters. Either one, either brightness equal to or less than 0, or brightness greater than or equal to 255. It's looking for both of those conditions, to one or the other, to be met before it executes what's inside of its curly brackets. Getting to understand the curly brackets and that these curly brackets relate to functions. This is the end of the void loop curly bracket. This is the end of the if conditional curly bracket. So making sure that these brackets are in the right places, and again that we're punctuating every line with a semicolon to separate them for the machine. And the delay that we have here, again, larger numbers make this slower, smaller numbers make it faster. And the fade value, again, you can mess with. It just has to be evenly divisible into 255 to avoid an awkward kind of jostle at the top and bottom of the cycle. But this is just doing the same thing as the last code, but with 3, and we're adding very little code to make 3 things happen instead of 1.
So here's the setup for our next set of code. This is something you've probably been able to create last week. We could say longhand, digitally writing high and digitally writing low, each one of these pins individually for a set amount of time. What we're going to do this week is make that same thing happen, but with a lot less code, using something called a for loop. A for loop is a logic loop that lets it iterate through a set of conditions, in this case a set of numbers, to make something happen in a series that makes it easier for us to code for the machine and make more complex things happen. Now, we're using 3, it could be 30, however many pins you have available to you, that's how many of these kind of things you can control. Especially with the for loop, it becomes so easy to code and so easy to manipulate.
So here we are in the for loop piece of code. Up at the top in our variables, well, let's just start by saying this is a pretty small section of code. This is it. This is all it is. It's not a long line of high, low, high, low, high, low. It's pretty concise, nice and condensed. So starting at the top, we've got our variables that we're dictating that are applied globally to the whole code. We've got our pins, 9, 10, and 11 for our LEDs, and a new variable called timer. Again, nothing is special about this word outside of us declaring that it's special with this integer designation in front of it up here in the global variables. So this could be timer, this can be yak, this can be glass, this can be scissors, it doesn't matter. It can be anything you want, and we're just telling the computer that it equals 100. We'll see why in just a little bit. In the setup, again, we're just designating, initializing our pins with the pin mode command as output pins. So it's not listening to them, it's outputting through them. And in the loop here, we have what's called a for loop. This for loop, you see the word for is gray, special. Inside the parentheses after it, it takes 3 arguments. In this case, we're making up a variable. In my case here, it's called anyPin. In a for loop like this, you can make up a variable on the fly that's only applicable to this for loop. So I'm doing that here. I'm declaring that this integer anyPin is equal to 9. The next piece of that argument is if anyPin is less than or equal to 11, the last argument, the third argument, is what to do. So we have our initial state of anyPin being 9. We have our limiting factor of anyPin being less than or equal to 11. And then the third argument is what to do between those two states. In this case, we have anyPin plus plus. What that means is take the value of anyPin and add 1 to it. That's all plus plus stands for. Take the number and add 1. So in this loop, it's going to digital write anyPin high. So anyPin, that's that special variable that's only applicable inside this for loop. The first time through, that anyPin variable will be the number 9. It'll delay, it'll stay on by how much the timer we've set at the top is, so that we can change it once and it'll apply every time. And then it'll turn it off and go through the next part of the loop, which is adding 1, so it'll be pin 10, the next LED. So anyPin in this next iteration of the loop will be 10. So it'll digital write pin 10 high, delay it, and then digital write pin 10 low, turning it off. And then through the next iteration, it'll be pin 11, ad nauseum. Because at the end of this, when it gets to 11 and it gets to the beginning again, it'll go back to 9, because that's the initial state of the loop. It'll start up again at the beginning and continue that way as long as we want it to.
So here's the operation of the next little piece of code. This is an example of 2 for loops working in conjunction. So in the last one, the run of the lights was red, blue, green, red, blue, green, red, blue, green, red, blue, green. In this one, it's bouncing back and forth. Red, blue, green, blue, red, blue, green, blue, red. And again, very easy to do with 2 for loops, working forwards and backwards, running through our pins, and everything else is the same. Let's go talk about the code.
So here's the next piece of code. It's the 2 for loop code. Essentially, we have what was in the original single for loop, followed by almost exactly the same thing, except what we've done is reversed the arguments of the first 2 of the 3 arguments of the for loop. So now that it's gone from 9 to 11 in the first loop, in the second loop it's going to go from 11 to 9. And instead of anyPin plus plus, we're just taking anyPin minus minus. Same thing in reverse. It's taking whatever the value of the variable anyPin is, and it's subtracting 1 until it gets to equal to or greater than or equal to 9. In the code below it, it's the exact same as the first loop. It's nothing different. Again, using the variable timer as our delay, which we can change up at the top. Longer stays on longer, larger numbers stay on longer, shorter numbers, smaller numbers stay on for a shorter period of time, and it's basically the same, just changing how it works with 2 different loops instead of a single loop. And always remember to check your curly brackets. Make sure that what you want in the first for loop is separated from what you have in the second for loop between these 2 curly brackets, and all of them have to live within the initial and final curly bracket of the void loop.
So for this next piece of code, we're going to add to this circuit just a little bit. We're not going to touch anything that's there. We're only going to be adding to. Let's grab our light-dependent resistor, one of our pigtail pairs that has the little jack ins, male jacks on one end, female on the other, so that we can plug in our light-dependent resistor. So we're going to need that extended out just a little bit, just to have some fun with it. So just jack it in. Those two pins are going to go one into the positive rail. Even though we don't have power to it yet, we're going to put power to it from the Arduino. And another one, we'll just choose a random row. Let's call it the last one here, number 30. Might start to get a little crowded on this end, so I'm going to take the ground jumper and bring it back. Plug it back into the negative slot, the ground slot. Ground, negative, all the same. New boards can be a little tight. Come on. There we go. Now I'm going to take a 5K resistor. It's the one starting with green, a green stripe, a 5K resistor. And we're going to put that between the same row, that number 30 row in this case. One of these jacks here, and back into the negative rail. There we go. Okay. Last thing we want to do is take our power, connect it into the 5-volt jack on the Arduino, and anywhere on the positive hot rail of our breadboard. Come on. There we go. The last thing we want to do is take from this very last row one more jumper from any of these points in the last row where this resistor and one of the two leads from the light-dependent resistor live. And we're going to bring it all the way to the other side of the board into pin A0. These are analog pins. You'll see the side of the board has analog written on that side. These pins, even though it's a digital device, it has a digital to analog converter that lets it simulate analog applications. So we're going to be analog reading the signal from here to control these lights. Let's go look at the code.
So here we have the code for our new circuit. We have a few new variables. Analog in, which is a new integer, and this is designating the pin that we're reading from the light-dependent resistor. It's designated as A0, capital A0. That's analog 0. Regular 0 is digital pin 0, so we have to differentiate it from the digital pin 0. The other new things are done at the bottom. We have two new integers, sensor and sensor 2. We're just initializing them as 0 for now, and we have two new integers, threshold 1 and threshold 2. These two numbers we can adjust to our liking as we see how the circuit works. The other new thing that we're doing here is we're using this command serial begin. This is initializing communication back to the computer at a 9600 baud rate. That's the speed at which it communicates. Don't worry too much about that. 9600 is pretty standard for now. The other new thing is we're designating our analog in pin as an input, not an output, just to be sure that the computer is listening to it and not trying to send things out of that particular port. If we go down to the loop, we have sensor equals analog read. So it's reading it in an analog fashion, looking for a varying signal. It's going to analog read our analog in A0 pin. It's going to take that reading, the sensor reading, and we're going to use this command called map, because what's coming out of the sensor is pretty raw and it can vary pretty widely. What we're going to do is say this new variable, sensor2, is equal to a mapping of sensor from 0 to 1028, which is what will be coming out of the sensor, and we're going to scale that back to a 0 to 300 range. So this map command is taking 5 arguments. What it's taking to map, what variable. The first 2 numbers are its expected range of input. The second 2 are the range at which you want to scale that input down to. So we're taking a 0 to 128 scale and shrinking it to 0 to 300, just to condense it a little bit. And then this next piece of code is what's going to give us some feedback into the computer. We're going to be using the serial print command to tell the computer from the Arduino, hey, what is the sensor 2 number? We're also going to be printing comma value separated numbers for the 2 thresholds to see where those live in relationship to this sensor number. Let's just look at what that looks like. We can go up to Tools and the Serial Plotter, and that'll bring up essentially a little graph. And if I wave my hand over the sensor, nothing will happen. There we go. It takes a little time to scale. So right now it's between, if you look at the left, it's a scaling amount. If we let this settle at one place for too long, it'll shrink it down to try to fit. But as I wave my hand in front of the sensor, it's showing me where the signal is. We can kind of see that signal varying up and down. And if I cover it all the way, I'll even drop down below that red line, which is our lower threshold. That's the 80 as opposed to 180, which is the higher level. So as you're doing this at home, test this out, see where your highs and lows are as you're covering this. Maybe you need to adjust what your thresholds are. But this is a good visual depiction of what those thresholds do. We're passing them below or above or in between. So I'm just going to put that down, close this, and let's see what those thresholds do. Down here we have 3 if conditional statements. So we just went over if conditions. So we know that it's asking itself, hey, if the sensor 2 value, which is the new scaled sensor 2 value, is greater than or equal to 0, and 2 ampersands means and, not just 1, 2, and sensor 2's value is less than threshold 1. If both of those arguments are met, if both of those conditions are met, then execute what's happening inside of the curly brackets of the if conditional statement. So if it is between 0 and the first threshold, we're going to light the first LED high. Now let's see, if it's in the second if condition, if neither of these are met, it moves on to the next if condition. If neither of these are met, it moves on to the next if condition, and since that's the end of our loop, it's going to return to the top and keep looking. So the next if conditional statement in the middle is asking if it's between the first or second threshold. That'll be lighting a different light. If it's between, in the last if condition, if it's between the upper limit of our mapping, which is 300, and the second threshold, it'll light a different LED. So we're setting up 3 different if conditions that it's going to be looking for, that we know all of our information lives within. We can look at our serial plotter just to check out what that thing is looking like. Let's go check it out again. If we give it a moment, there we go. And as I wave my hand in front of it, it'll start to vary the signal coming out of the sensor and light different LEDs in response to that signal and its relationship to the thresholds. So one LED is on versus another versus another. And depending on how you set up your lights, it'll be a different light. So now let's go see how this looks on the board itself.
Alright everyone, so we've got our circuit hooked up with our light dependent resistor. We've got this secondary resistor making a voltage divider with this one. I'll explain that next week. Needless to say, this last row shares one leg of both the light dependent resistor and the regular 5K resistor. One leg of the light dependent resistor is going into positive, One leg of the static or just regular resistor is going into negative, and we're going from that same row, the last row, back to pin A0 on the analog side. So now, as I wave my hand in front of this light-dependent resistor, we should change what's outputting from these LEDs based on that amount of light. So the closer I get, the more light that I strangle from this thing, it'll change how it outputs. So you could kind of think of this as a touch switch. This could be some sort of sensor in a sculpture. These outputs currently are LEDs, but if we can turn on LEDs, we can do a lot of stuff as we get more sophisticated. So play around with this. If you need to adjust your thresholds based on the amount of ambient light in your particular workspace, do so, and use the serial plotter to figure out where those numbers need to be. Pretty fun.
So the last thing I'd like to show you is how to import these files that I'm going to attach to the upcoming email into your Arduino program. So you'll download this folder that I'll attach, and inside it has all these other folders, and all of these other folders each individually contain one piece of code that we've worked on. I have notated and unnotated examples of each just in case the notes get in your way. But each one has to live inside of its own folder with the same name as the code that's inside of it. So once you download this, you'll have this inside of it, and wherever, when you started up your Arduino program, you told it, hey, make a file somewhere to store all my code. Mine is in Documents, Arduino. In that file, you'll have all of your sketches in files themselves with the same name. So what we can do is open up the file that you'll download from me, grab them all, drop them in here, and now you can open them from your Arduino program. It'll be in your sketchbook, and you'll see analog read notated, yada yada. So that's just an easy way to get them all right into your computer, right into your board without doing much work.